Good evening and a very warm welcome to expert speaker and participants joining us today. On behalf of the Department of Electronics Engineering, MIT's deemed University Gwalior, I feel honored to welcome you to the day 4 of AICT sponsored Atal Online Faculty Development Program on Emerging Frontiers in Quantum Technology and Communication. Once again, I request all participants to please kindly keep their microphone muted. It affects our quality of the recording and use the chat box for technical queries. For today's first session, we are pleased to have Senior Professor Dr. T. Ratnaraja. Good evening, sir.
Good
A
evening.
very warm welcome to AICT sponsored Atal FDP. Thank you for joining us. It is my great privilege and honor to introduce today's distinguished speaker, Professor T. Ratnaraja, an eminent expert in the field of communication system. Uh, Professor T. Ratnaraja works as a Fred Harris Endowed Chair in Digital Signal Processing at San Diego State University and Director of the Communication System and Signal Processing Institute. His research interests include signal processing and information theoretic aspect of beyond 5G networks, full duplex radio, millimeter wave communications, random matrix theory, big data analytics, and machine learning for wireless networks. He has published over 475 peer reviewed papers in these areas and holds 4 US patents. He was the lead coordinator of the European Union project HARP in the area of highly distributed MIMO and ADL in the area of the licensed shared access. He was also the coordinator of the European Union Future and Emerging Technologies project that is crowned in the area of cognitive radio networks and HIATUS in the area of the interference alignment. Professor Ratnaraja was an associate editor of IEEE Transaction on Signal Processing during 2015 to 17 and technical co-chair of the 17th IEEE International Workshop on Signal Processing Advances in Wireless Technology in 2016. Professor T. Ratnaraja is a fellow of the Higher Education Academia. Respected sir, participants are looking forward to your talk. May I request you to please begin the talk?
Okay, thank you, Mukesh, for your kind introduction and your invitation as well. So, I think you can see my slide, yeah?
Yes, sir. Yes, sir.
Okay, so today's my talk is Federated Learning in Massive MIMO Networks, Convergent Analysis and Communication Efficient Design. As Mukesh said, my name is Ratnarajah. And welcome all of you to my talk. Okay, so before I start talking about my topic, I just wanted to talk about general introduction to federated learning. So we all witnessing the rapid evaluation in the field of machine and deep learning during the past few decades, or maybe at least one decade, along with the tremendous application, including computer vision, natural language process, and medical image analysis, etc. For proper working of machine or deep learning based application, it's require powerful machine with a huge computational resources and significant amount of data in order to learn a reliable model. So in order to learn a reliable, deep learning algorithm, you need a very big, powerful computer resources, and you need a large amount of data, which not only incur high cost, but also damage the privacy of the data. While sharing the data, it also damage the privacy of the data. So recently, people have introduced a technique called federated learning, where your deep learning algorithm will learn the model without sharing the data. So you learn the model without sharing the data. So that is called distributed learning or federated learning. So my talk is about today, how do we, do a federated learning in the 5G network, especially 5G networks are now equipped with massive MIMO base station. So how the learning, distributed learning is happening in the 5G network, and what are the things affecting the convergent analysis of the learning algorithm. So that's my topic today. So how do you do a distributed learning over a 5G network, which is the massive MIMO network? Okay, how the fading and noises and interference and quantization, etc., affecting the convergent analysis of the distributed learning. So that's my topic today of talk. So, with that small introduction, so this is the overview of my talk here today. So, I will start talking about federated learning and the system model. Then I will talk about convergent analysis and communication efficient design, and then I will show you extensive simulation results, and then I will talk about concluding remark, and I will show you some our recent papers on this topic. So, as I mentioned, federated learning is an emerging distributed learning algorithm utilizing computer resources of decentralized device. So, and user data never leave their device, hence preserving the local user privacy. So, the federated learning is the privacy preserving distributed learning algorithm. So, you learn the model, but your data is never shared or never leave the device. So for example, if you there are some, let's say, 10 users wanted to learn a classification algorithm or something like that. So they all have data, but they don't want to share the data, but they wanted to learn the model. So that is the concept of federated learning. So you learn the model without sharing the data. So it's a privacy preserving distributed learning algorithm. Okay. So different learning tasks can be accomplished, such as image classification, regression, natural language process. Any task can be learned in a distributed measure. So we are considering average-based federated learning algorithm in this study. The key ingredient of our work is we consider, as I mentioned, 5G network, which is a cellular network equipped with massive MIMO. We consider zero forcing and MMSE precoder and combiner. We consider both IID and non-IID data sets. Okay. So this is the system model. I'll spend some time to explain this system model. So you can consider like a single cell cellular system. Here is the base station equipped with massive MIMO system. There are, let's say, end users here wanted to participate in this federated learning algorithm. So these end users, they all have their own computer resources, and they also have their own data set as well. Okay, but these data sets they don't wanted to share, but they wanted to learn the model. Okay, so in the traditional one node learning system, you share all the data in a one place, and you use a powerful computer to learn the model. Okay, learn the machine learning model. But here we learn the model distributed fashion. We never share the model data, but the data never leave the device. So each but the model is learned in a distributed fashion. Okay, so that's what. So each user have their own computer and own data set, and they learn the model without sharing the data. Okay, so I hope you got the idea of what is federated learning. So here's the timing diagram here. So each user start do a local training using the stochastic gradient algorithm. So they try to do let's say S1 number of iteration in each of these own devices using their own CPUs or GPUs and own data. They do a um, local iteration using stochastic gradient algorithm. At time S1, let's say after 10 S1 is a 10 iteration, let's say after S1 iteration, they send the model weights to the base station. Okay, so the machine learning algorithm, the model weights are real. So these real weights are quantized and then mapped to a complex symbols like a QPSK or QAM modulation, and then it is sent through uplink channel to the base station. So all the users do S1, let's say S1 local update, and then quantize their model and map to a constellation. And maybe if they have multiple antenna, they do pre-coding and send it to the uplink channel to the base station. And then the base station have a massive MIMO system. We consider a 5G system. So massive MIMO antennas are here, base station equipped with massive MIMO antennas. They receive the signal and they decode the weight and then they do some weighted average at the base station. So all the user weights are received at the base station. They do some kind of a weighted average or normal averaging, and then they transmit that weight again, quantize the weight and map to the constellation and do pre-coding and send back to the users using the downlink channel. Okay, so this is the process here. So timing is S1 local iteration, then the red color arrow is showing the uplink communication, and then base station do a model aggregation, and then the blue arrow shows the downlink communication, and then the users got the updated weight, and they do again a local iteration, another S2 number of local iteration, and send it back and etc. So until the model is converged, they do this kind of uplink downlink communication and local iteration, etc. Okay, so what we are going to study in this work is to how this wireless channel introduce errors as well due to fading and interference, and you are also quantizing the model weight as well, so that introduce some quantization errors, etc. So how all these impairment affecting the convergent analysis. So that's the one we are studying here. So federated learning over 5G network, how it's the performance is affected by the communication errors, and also we wanted to design a system that is most cost efficient model as well. We don't wanted to do a lot of uplink downlink communication, so we wanted to want algorithm to converge very quickly. So we wanted to find an algorithm that lead to a communication efficient learning algorithm as well. So that's the purpose objective of this work. Okay, so I'm going to show you the system model, and now some equations are going to come here as well. So let's say the kth user, one of the user, store local data sets, let's say DK data sets. These are the data point. The size of the data set is, DK. The data set is denoted by curly DK here. Each of the data point, training data point D is stored as a input output pairs. This is input and this is the output of the model. Let's say if you wanted to learn a classification algorithm, X is the input, Y is the output. Where X is the input to the model, Y is denote the corresponding output. The total data set of all the users within the cell can be defined as a capital D is a summation of all the user data set. Okay, so the size of the data set is the capital D. So let's FWD is the loss function. In the machine learning algorithm, the loss function that we used is sum of mean square or cross entropy loss function. Okay, so this is the loss function. Denote the loss function to measure the loss between the model output based on W label data D. For the k user, the loss function is calculated over all its user training data set is defined by this. So the k do use the loss function is defined by this equation here. So the overall loss function for the data dk for all the users can be written as this equation here, equation number 2. Okay, so where the alpha is defined by dk over d, and the alpha satisfy this equation as well. So the objective of the federated learning is to find a W that minimize this FW. So objective of the machine learning algorithm is to minimize the loss function with respect to W. So we wanted to find a W that minimize this loss function. Okay, in this case, we wanted to find the W distributed fashion that minimize this cost function. So that's the objective, and we wanted to do it very quickly, find this minimum, and also we wanted to do it in a communication efficient manner as well. Okay, so a little bit more on the system model here. That's time instant for each communication round is given by this diagram here. This is the time instant the communication is happening. As I said, at time S1, uplink communication happening, and time S1 plus S2 is another uplink communication happening, etc. So the local iterations happening S1 time and then another S2 time, etc. So instead of for the local update is the total time subtracted from the communication time. So that's the time the local iteration is happening. Okay. Uh, the curly T is selected uniformly. We can do same amount of local training each time as well. Let's say 10 local iteration each time the user will do a 10 local iteration, or it can be changed. At the beginning, you do a lot of local iteration, and when the model is converging, you do less iteration at the local iteration, etc. We can do uniformly the local iteration. That means SR is equal to S, or non-uniformly. At the beginning, we do a more local iteration. At the end, we do less local iteration, etc. We study all these effect in the conversion analysis in this work as well. So the kth user performed the local stochastic gradient algorithm using this equation here. Here is the weight and neta is the learning parameters. We are using, each user will use not only all the data set, maybe a subset of data set as well. That's why it's denoted by psi k as well. So, so here, the next few slides, I'm going to show you some equations, the communication equation, the zero forcing precoder and zero forcing combiner equation, etc. So let's say the received signal at the base station site can be, so all the users, K users do a local training, S1 local training, then they quantize the real weight and then map to a constellation co-modulation or whatever, and send it to the base station. So the base station receive the signal. This is the received signal at the base station. There are end users, so that's why there are summation from 1 to n users, and this is the channel, this is the weight of the users, and this is the P is the uplink power, and Z is the noise. Okay, so we are considering, as I said, zero forcing combiner, where, in traditionally zero forcing combiner or base station can do also MMSE combiner as well, or they can do a maximum ratio combining as well. We consider zero forcing combiner. It's because it's performed well, and also is we can analyze mathematically very easily as well. If you use a, MMSE combiner, the performance is a little bit better than the zero forcing combiner, but MMSE receiver, if you use the mathematical analysis, is not easy to do. Okay, the convergent analysis is not easy to do. So that's why we are using a zero forcing receiver here, and this is the estimated weight at the base station. It's given by the true weight and some estimation error. Okay, so this is the estimation error. So in the next few slides, I'm going to study the weight error variant. Okay, the estimated weight error variant. So that error variant equation is very important in the conversion analysis. Okay, so we are next few slides. I'm going to show you how do we find the estimation error variant. Okay, so that's a little bit more complicated equation, but I will explain as much as I can. Okay, so this is the estimate base station estimated weight, and it's a true weight and plus some estimation error. Okay, so each of these, this is the matrix. Each of these column have, so I'll show you here. The matrix H is this matrix H is this matrix H is a concatenate each of the user channel matrix. This is the each of the user channel weight, each of the user model weights here. So I told you this, this is the error matrix, have a each of these column have a, each of the column of the estimation error term has a zero mean, and the covariant matrix is given here. Okay, this equation here. So what I'm saying is this estimation error matrix columns have a zero mean, and the covariant matrix is given by this expression here. So now we are going to use the Massey MIMO results. So if you, when you use Massey MIMO system, there is a concept called channel hardening. So what does that mean is if you use a large number of antennas, owing to the channel hardening, this term is approach to identity matrix. Okay, by using this MIMO channel hardening results, we can simplify the covariant matrix of the estimation error to like this. So the covariant matrix of the estimation error is turned out to be this equation here. Okay, so so what does this mean is, so the each use of model weight estimation at the base station is a true weight and sum of the estimation error. That error have a zero mean, and the error is distributed as a Gaussian, and it have a zero mean, and the variance is given by here. Okay, the factor 2 is coming because we are the model weights are real, and we are changing to complex constellation. Because of that, there is a 2 also coming here. Okay, so this is the estimation error due to uplink. Okay, due to uplink, which is the estimation error is a Gaussian distribution, and the zero mean and the variance is given by this equation, this term here. So, okay, so then the base station estimate the weight, and each of the user weights is estimated at the base station, and then base station will do a averaging effect. It's do a weighted averaging or whatever. It's doing the averaging. While doing the averaging also, there is a error introduced as well. So this is that error. That error variant is given by this expression here. So this error, the base station aggregation also lead to some estimation error because of the quantization, etc. That error variant is given by this expression here. So as you can see, I am trying to form, try to find the estimation error variance, because that will influence the conversion analysis of the federated learning algorithm. Okay, so now I found the error variant of the uplink communication. I found the error variant of the aggregation effect, due to aggregation effect at the base station. Now I'm going to find the error variant due to downlink communication. Okay, so this is the downlink communication. In the downlink, we use a zero forcing precoder at the base station, and the estimation, the user. The downlink channel, the weight estimation is again, this is the true estimation is going to be the estimation error is term is here. This is the estimation error due to downlink communication. Again, we're using the massive MIMO results, channel hardening effect, the estimation error covariant matrix. So the columns of this covariant matrix is given by this expression here. Okay, and again, we can show due to downlink communication, the error have a error variant that is also the error is distributed as a normal distribution and zero mean, and the error variant is given by this expression. So these are kind of our contribution here to try to derive this error variance. Why we want this error variant is this error variant is the one is going to affect the conversion analysis of our federated learning algorithm. Okay, so now I'm going to put everything together. So function pi k represent the distortion arise due to uplink, downlink communication, which can be decomposed in uplink distortion, averaging effect, distortion due to averaging effect, and the downlink distortion as well. So we can put everything together. This is uplink distortion, averaging effect distortion, and downlink distortion together, and we get the weight W of the kth user and some estimation error. I'll show you the total error variant equation in a minute, but we derive the total estimation error weight variant due to uplink, downlink, and averaging effect all together. Okay, the combined effect. Okay, so now I'm going to show you some theoretical results about the convergent analysis. As I said, the machine learning algorithm use, the loss functions, typical loss function the machine learning algorithm uses, sum of mean square error, or cross entropy loss function. These loss function satisfy all these assumptions. So you may, if you study the, convex optimization techniques, etc., you may see this assumption. These assumptions are a standard assumption. Let's say that each loss function of the each user, let's say this can be a sum of mean square error or cross entropy loss function. They all L smooth. So L smooth mean given a two weight V and W, they satisfy this inequality. So the L is appear here. So this, if the weights W and V satisfy this equation, and these functions are called L smooth. Similarly, these functions are called mu strongly convex. Given a two weights, they satisfy this inequality. The mu is happening appear here. This appear here. So if the loss function satisfy this inequality, we call these loss functions are mu strongly convex. The next assumption is called bounded variant for the stochastic gradient algorithm. So the variance of the stochastic gradient satisfy if this inequality we call the bounded variant stochastic gradient descent algorithm. So the gradient will be the bounded. There's another assumption. It's called uniformly bounded gradient. If the gradient satisfy this equation, we call uniformly bounded gradient. So these assumptions, as I said, is a standard assumption. If this assumption satisfied, it's normally going to satisfy for any machine learning algorithm using sum of mean square loss functions or cross entropy loss function. Then we can get a convergent analysis expression easily. Okay, so another theoretical results for uplink downlink imperfect communication given any model W, the L2 norm of the model error is bounded by this expression. So here we are showing the while doing the iteration, the L2 norm of this weight is upper bound by this expression here. So that means the weights are converging, is not diverging. So as I told you, I will show you the total error variant. This is the total error variant here. So you can see the error variant have a very complicated equation. We derive this error variant expression using the concept of Messi MIMO, the error variant expression simplified to this expression here. Okay. So here we are showing the weights are bounded, it's not diverging. Each when you do this iterative um, um, when you do this many communication round, it will eventually converge uh, to the global model weight or whatever. So here is all these results are published in these papers. If you wanted to see that proof of all these equations, you can see it in this work here. So there's another results we needed before showing the convergence analysis results. So let's assume 1 to 4 hold. All these assumption that I show you is hold. Then with respect to optimized model weight, W, the L2 norm of the next step model update error can be bounded by this. Okay. So each of these, what this lemma is saying is each of these update, the model is converging, it's not diverging. By properly choosing these nitas as well, these nitas are the learning rate of the stochastic gradient algorithm. So this is our main results. So if the assumption 1 to 4 hold, the sigma, the total error variance is defined as here. The proposed Federated algorithm satisfy this convergent results. Okay, so the neta is defined by here, and the C is defined here. The C is defined here. This is the error variant. You can see from this error variant, we can get some insight. For example, this PDL is the downlink power. So the downlink power, if you have a large downlink power, then the variant of the error will be reduced small, then the convergent analysis algorithm will converge very quickly. So I'll show you some results. So the theorem 3, this theorem, main theorem of the convergent analysis, tell us that the modeling error of the federated algorithm reduced in the order of t to the power -1 and the sigma squared. Okay, t is the number of iteration. If when you increase number of iteration, it will converge faster. Okay, so this is the main theorem of the convergent analysis theorem. We show this federated learning algorithm by appropriately choosing in the nitas and etc. It will converge rather than diverge. Okay, so next I'm going to show you some study about the communication efficient design. In the title, I told you that we are proposing a communication efficient design. So the communication cost of this federated algorithm is depends on there are few parameters. So the overall communication cost is the number of communication round, into a number of model parameters, into normalized transmit power, and a number of quantization bits. So the total cost is depends on how many time you do a round communication round, how many model parameters that you have, and normalized transmit power, and the quantization bit. If you do use a large quantization, your cost also going to be large as well. Okay, so this is the our proposed communication efficient federated learning algorithm. So this is just an initialization part, and this is the downlink part. This is the downlink transmission. Base station quantize the model weight and transmit downlinkly. We also consider power allocation using this expression here. What is this expression is saying is you use less power at the beginning when the algorithm when the algorithm running, you increase the power according to this expression here. So what is this? Why we are using this why we are using this expression is use less power because we want a communication efficient federated learning algorithm. So we use less power at the beginning. When this algorithm converge, we increase the power, because when the algorithm is converging, we don't want it to make any error. Okay, so at the beginning less power, and at the end we use high power such that it converge. The algorithm is more efficient as well, cost efficient as well. So this is the way the power allocation is happening. And this is the downlink communication effect. And here is the uplink. Uplink also we are using power allocation at the beginning, less power, at the end larger power is used as well. Okay, so this is the uplink communication steps, and here is the some user selection. In the federated learning algorithm, there are end users participating. We can also select reduce the number of users they are in the system as well. Okay, so people have studied different way of selecting the users. You can select the best K users, having a good channel between the base station and themselves. So they those users may be selected for the federated learning algorithm, or you can select the users that need more time to converge. Okay, we check the model weights with the previous iteration, and if they are very large and need more iteration, we choose those users to participate as well. So there is a user selection also we can do during the learning as well. So anyway, so this is our communication efficient federated learning algorithm. As I said, this part is the downlink part, this part is the uplink part, this is the user selection, and this is the the stochastic gradient algorithm at the local steps. Okay, so I'm going to show you some extensive simulation results now. We consider three data sets. One is called MNEST data set, and other one is fashion data set. The MNEST and the fashion data set, they have 10 classes to classify and extended. They are in the MNEST data set, everybody may know, there is a 10 hand written digit from 0 to 9. Fashion MNEST is the 10 cloth data classes. So the MNEST and the fashion MNEST is the 10 classes to classify, and extended MNEST is the handwritten letter of 26 letters. So there are 26 classes to classify. So it's a bigger class. So this we consider all three data set. So we consider our simulation 25 users. We consider massive MIMO base station with 128 antennas or 64 antennas. Each user training sample is 50. We consider 15-layer CNN network. So the classification algorithm using 15-layer CNN algorithm. Communication step is 100 global communication round. The CSI is known at the base station. The channel is relay fading channel. What else I wanted to say here? Okay, as I said, the uplink power is allocated according to this equation. The downlink power is also allocated according to this equation, etc. Okay, so with this simulation setup, I will show you some results here. So this is the testing accuracy versus global communication round. Okay, so this is at the user side. Okay, testing accuracy of the training process at the local user side. Okay, so what is this different curves? The green line is the it's a perfect case. There's no communication error, no quantization error. Everything is perfect. So okay, so this is the perfect case. Is the green line. So this is the testing accuracy versus global communication round. And we are and the different color curves are for the different uplink SNR. Okay, so this is the uplink SNR is minus 8 dB, and there is a magenta color very close to green, which is the uplink SNR is minus 3 dB. Okay, so you can see and the downlink SNR is fixed to 10 dB. Okay, so here we are showing the local user testing accuracy. Downlink SNR is fixed to 10 dB, and the uplink SNR is changing, and we can see minus 3 dB downlink SNR is good enough to get the best result compared to the perfect case, which is the green. Okay, so we need a downlink SNR is minus 3 dB, uplink SNR is minus 3 dB. So you may wonder why is very low SNR. Things are working because of the massive MIMO system. Massive MIMO system have a large array gain, so it is it will perform better at low SNR as well. So that's why. So we can from this results one conclusion is the downlink SNR we need a 10 dB, uplink SNR we need a minus 3 dB to get a good accuracy. Here is the testing accuracy again at the local user, and we now we fix the uplink SNR to minus 3 dB. We found here minus 3 dB uplink SNR is good enough, so we fix the uplink SNR to minus 3 dB, and we change the downlink SNR. Again, the green one is the perfect case, and you can see the magenta color of 10 dB is very close to the green one. So we need a 10 dB downlink SNR, and the red one is 60 6 dB SNR, and we can see is we need a 10 dB downlink SNR to get a good performance. Okay, so by doing this kind of study, we find out what is the signal to noise ratio that we require for uplink and downlink. Okay, so that's one of the conclusion here. Okay, so here we are showing the testing accuracy versus uplink SNR. Before we studied in this paper, some other publication in the literature studied the downlink communication is error-free. So what is this I'm trying to say here is, the other before we publish this paper, there are some other group studied this federated learning and convergent analysis, etc. They assume the downlink communication is error-free communication, because the downlink is very important. From server to user communication, they assume error-free. The server to or the base station to the user makes some error, then the conversion of the model is very unlikely. So that's why the people notice that, and then people have studied assuming that downlink is no error. Okay, so that is the results of this black curve. Downlink zero forcing, downlink error free is the black curve. So this is the people assume before our study the downlink is error free. But we can see with the downlink of 10 dB, we consider downlink is also error can happen in the downlink as well. So we can show here the error-free case and the error case with the 10 dB is performing almost same. So instead of assuming error-free downlink communication, we can say if you have a 10 dB SNR in the downlink, then the performance both is going to be same. So that's a kind of a conclusion from these results. So this is the testing accuracy versus uplink SNR. We need uplink SNR is about 4 dB or something like that. Then minus 4 dB or something like that. Then the conversion testing accuracy is good enough. Okay, so we can the contribution of these results is to find out what is the SNR, what is uplink, downlink SNR, etc. is required to get a good testing accuracy. Okay, here all these results are for the MNEST data set, IID data set. Okay, if there's a different data set, I will let you tell you. Okay, all these results are MNEST data set. Okay, so I told you we consider zero forcing combiner in the performance analysis because zero forcing is we can analyze mathematically easily, derive this error variant and conversion analysis easily if we use zero forcing combiner or zero forcing precoders. But we all know MMSE is performing better than the zero forcing. But MMSE is difficult to analyze mathematically. Okay, so in the analysis we use zero forcing, but the simulation we also use MMSE as well. You can see MMSE is the blue curve and the zero forcing this magenta color, and MMSE is performing better. So testing accuracy versus global communication round, we consider the SNR, uplink SNR, downlink SNR is 8 dB, and uplink SNR is minus 8 dB, etc. The base station have 64 antennas as well. Okay, so the purpose of this that MMSE per combiner and precoders are performing better compared to zero forcing precoder combiner. Okay, so here I told you we can also select the number of users participating in the federated learning algorithm. You can see here, this is the full participant. Every users are participating in the learning, and the red curve is the uplink channel state based selection. We select the users with the good channel users are selected in the learning algorithm. So that is the red curve, and the blue one is the L2 norm user selection here, and both are performing almost same. And if you have a large number of users, then the learning is giving you a better testing accuracy. Okay, so here this curve, this is the testing accuracy again, and here is the loss function. Here is the loss function. Okay, so this side is the loss function, and this is it is a testing accuracy. Here the x-axis is a communication round. So the blue curve is okay. The blue curve is a fixed SNR. So I told you we can also change the SNR, uplink, downlink SNR according to our equation, power allocation equation. So the blue curve is we don't use power allocation. We always use fixed SNR. The black curve is here is the varying the SNR. Okay, so you can see if we use a fixed SNR, the accuracy of the testing accuracy is good compared to the varying SNR. But the fixed SNR will give you more cost compared to the varying SNR. Varying SNR is less cost effect compared to the fixed SNR. Here you can see again the red one is the fixed SNR. The loss function is giving a very less value here compared to varying SNR, which is the magenta color, and the green one is our theoretical results. We can see the green one, our theoretical conversion cost function is converging results that we derive. That is the green one, which is the theoretical results is matching with the simulation results as well. Okay, so the conclusion of this figure is if you have a fixed SNR, then accuracy is better, but the cost is high, okay, compared to the varying SNR. So this table is showing different quantization. I told you the model weights are real and we need to quantize when you do transmission to uplink downlink. So this is a different quantization: 10-bit quantization, 12-bit quantization, 14-bit quantization, and 16-bit quantization. Here is the varying the local step. We also fix the power, varying the power, fix the power, fix the local steps, varying the power, fix the power. So all these different scenarios are we simulated. This is the testing accuracy. You won't see much different. This is for the IAD training data set as well. So you can see varying power or the fixed power is not giving not much different. They are all performing almost same here. But of course, when you increase the quantization, you getting the better performance compared to 10-bit quantization compared to 16-bit quantization. Okay, so here we consider non-IID data set. What is the non-IID data set mean? So in the user data sets, some of the letters are more, let's say MNES data set, you have a handwritten letter of 0 to 9. Some of the letters are more occurrent compared to the other letters. So let's say there are 0 to 9 handwritten letters. Let's say some of the letters, let's say 5 or 6, can occur more compared to the other letters. Okay, so each of these letters are not equally likely. So that kind of a data set we call non-IID data set. Again, we consider non-IID data set here for different quantization bit. You can see here varying the power, fixed power, there is a big difference for the non-IID case compared to IID case data set. Here is the both are very equal. Here is you can see a small different here for the fixed is performing better, and of course if you increase the quantization bit also performing better as well. Um, and here also, when you fix the local step, is also performing better as well. Okay, so here testing accuracy versus global communication round. Here is the different non-IIDness. Okay, the green one is the IID data set. So each of the local user data, each of these letters, 0 to 9 letters are equally likely. And here is some non-IID. Some of the letters is more occurrent than the others. So you can see if you increase the non-IIDness, the performance is testing accuracy is less. Here is the non-IIDness for the black curve is 90. IID case is green one. You can see non-IIDness reduce the testing accuracy. We also use different quantization. So we use uniform quantization. So as I said, the model weights are real weights. We need to quantize before transmission. We use uniform quantization, or we use SR, means stochastic rounded base quantization as well. So the uniform quantization use 16 bits, and stochastic rounded base quantization use 8 bit. And you can see there are two curves. One is the non-IIDness 70, other one is 90. So this is the uniform. This is the uniform quantization using 16 bit with the 70 percentage non-IIDness, and the blue one is using the same non-IIDness, but is use only 8 bits. So the results is showing the stochastic rounded quantization is better compared to uniform quantization because it's used only 88 bit as well. And when you increase the non-IIDness to 90%, the performance reduce. Okay, so the basic conclusion from these results is stochastic rounded uh, uh, quantization perform better compared to uniform quantization because it's used only 8 bits, but the performance is almost same compared to 16-bit uniform quantization. Okay, so here I'm showing three different data sets. Okay, these black curves are showing the MNEST data set, performance testing accuracy. This is MNEST data set. As I said, there are 9 classes to classify, and the blue curves here are the fashion data set. Fashion MNEST data set, and this performance is degraded compared to the MNES dataset, because the fashion dataset, all the 10 classes of the clothes are very similar. So that's why it's performance degraded. And these curves are for the extended MNES dataset. Again, this performance is further degraded as well, because there are 26 classes to classify. These two are only 10 classes, and here is the 26 classes to classify. Its performance is, degraded compared to these data sets. Okay, so again, these two curves are for different downlink SNR. The top one is 8 dB and the other one is 7 dB. Again, yeah, so we consider 64 antennas, base station antennas, etc. Okay, so that's all I wanted to say in this talk. So this is my conclusion slide. We have analyzed the federated learning algorithm in multi-user massive MIMO cellular network. We consider imperfection at the uplink, downlink, and we consider zero forcing and MMSE scheme, and this MMSE and zero forcing receiver null the co-channel interference as well. The tight convergent bound on the modeling error has been derived, incorporating this imperfection due to uplink, downlink, and quantization errors, etc. The conversion algorithm is converged in the order of t to the power -1 and sigma squared. This is the total error variance. Sigma squared, that is the total error variance. We saw the downlink SNR and the uplink SNR could be increased as the raining goes on, motivated by which improve the communication efficiency of the system by adjusting the local training step, transmit power, and quantization bit. We saw that compared with the reliability of the uplink, the quality of downlink play a more significant role as well. So the downlink communication, or the server to user communication, the federated learning is very important. If you make an error in the downlink or server to user communication, then your algorithm may not going to converge. So the downlink is very important. Okay. Simulation results for the image recognition task with MNES and extended MNES and fashion MNES datasets have been verified the theoretical insight for our results. Okay, so that's all I would like to tell you today. And here, these are some publication we have done recently in this federated learning algorithm, or federated learning research. The paper that I presented in this talk is this is the paper that we presented. We have some more papers after that published, federated distillation in the massive MIMO network. We have published, we have present those results in the ANS tutorial on Monday. We have some more work as well. We recently published, which is adaptive model pruning and personalization for federating over wireless network. This is our recent work. This is also we have presented in the ANS tutorial on Monday as well. So here we use model pruning, some the model with a less weight prune as well, and we try to do efficient communication efficient federated learning algorithm as well. Okay. Okay, so if you are interested in federated learning, so you could look at our three recent papers in these three journal papers that we published. Okay, thanks, guys. That's all I would like to say. Thank you for listening. I am happy to take some question if you have, and yeah, that's it.
Participants, if you have any question, you can type in chat box or that you can ask. Sir, in chat box there is one question.
Okay.
Question is, how do wireless channel impairments affect convergence and reliability of federated learning?
Yeah, that's what we have studied how the wireless channel imperfection and affect the conversion analysis. That's what we studied, and that's what I presented. So if you okay, so in terms of answering this question, if you have a large downlink communication errors, for example, if your server to user communications error is high, you may not able to converge. The model may not be learned properly. You won't get the convergence. Okay, so that's the one of the observation. The downlink communication is very important. And second is, of course, if you increase the quantization bits, is you will get a better performance. By increasing the quantization bit, you need to do uh, high data rate communication, so your communication cost will be increased as well. So yeah, these are the some of the observation. Yes. Any other question?
Any other question, participants? Okay. Okay, sir. Thank you so much for this interesting and knowledge enriching session on federated learning. Uh, Once again, thank you so much, sir, for your kind support and participations in Atal FDP on emerging frontiers in quantum technology and communication. Thank you so much, sir.
Okay then, Mogesh. Thank you. Bye.
Okay, sir.